Today, we're going to cover one of the most misunderstood topics in math, the logarithm. But before we dive into what the log actually is, we need to take a step back and understand this simple looking equation. A to the power of b is equal to c. It might seem basic, but it's the key to understanding exponents, roots, and logarithms all in one. Let's break them down one at a time, starting with the exponent. Depending on which variable we're solving for, we get three different types of problems. First, if we're solving for c, we get the classic exponent. So let's go ahead and look at an example of this. 2 to the power of 4 is equal to x. Here, x is just a variable that we're solving for. Breaking it down, 2 is the base, 4 is the exponent, and we're solving for the result, which is c in our equation. To solve for c, we multiply the base by itself however many times the exponent says. So in this example, we multiply 2 by itself 4 times. 2 times 2 times 2 times 2, which is equal to 16. Formally, we could say the fourth power of 2 is equal to 16. And we can look at other exponents of 2 as well. The third power of 2 is 8, the fifth power of 2 is 32, and the seventh power of 2 is 128. In the original case of 2 to the power of 4 is equal to 16, we see that a is equal to 2, b is equal to 4, and c is equal to 16. This is what most people picture when they think of a to the power of b is equal to c. We think of the exponent first. But we still have two other variables we can solve for. So let's go ahead and move on to roots. What happens when we want to find a, the base, and we already know what the exponent and the result are, or b and c? This brings us to the roots, also known as radicals. We'll skip the formal terms for now, but the core idea is this. We know the exponent and the result, but we don't know what the base is. So let's go ahead and look at an example of this. X to the power of 4 is equal to 16. To solve for this, we use the inverse of the exponent, and then we can rearrange the equation, like this. We get a is equal to c to the power of 1 over b. So now we ask, what number raised to the fourth power gives 16? And the answer is 2, because 2 to the fourth power is 16. This is the same example as last time, but now we're looking at it from a different perspective. We can also write it as 16 to the fourth root is equal to 2. Let's try another one. The square root of 64 is equal to x. So here we're solving for the square root of 64. Most of the time, you'll see radical problems written like this, and you won't have to manually convert them from the exponent form like we just did. Also note, when there's no number written above the radical symbol, it's assumed to be 2, and that's what we call the square root. So we're asking, what number multiplied by itself twice gives 64? And after thinking about it for a couple of minutes, we can see that the answer is 8. 8 times 8 is equal to 64. So when we use roots, we're solving for the base, or a, in the equation. That is our unknown. Now let's go ahead and jump into logarithms. This time, we know that the base, a, and the result, c, are some number, but we're missing the exponent, b. This is exactly what logarithms are built to solve. To take the logarithm, we rewrite the equation like this. Log base a of c is equal to b. Let's go back to our earlier example, 2 to the power of x is equal to 16, our exponent problem. And now we're going to shift the unknown to x being b. We're asking, how many times do we multiply 2 by itself to get 16? And here the answer is 4. 2 to the power of 4 is equal to 16, or log base 2 of 16 is equal to 4. So again, how many times does 2 multiply by itself to give us 16? Now that we've seen all three forms, let's tie them together a little bit. At the center of all of it is the equation a to the power of b is equal to c. And depending on which part we're solving for, whether we're solving for c, which will give us exponents, A, which gives us roots, or B, which gives us logarithms, they're all one equation. They're three unknowns and three perspectives, kind of like a triangle. Let's go ahead and work through a couple more logarithm examples just to really solidify the process. Here we have log base 10 of 1000. So we're asking ourselves, 10 times itself, how many times is equal to 1000? So here the answer is 3, since 10 to the third is equal to 1000. This is a really common base to use. Often we'll use base 10, base 2, or the natural base e. Let's go ahead and look at another example now. Log base 3 of 81. What power of 3 gives us 81? Here the answer is 4, since the 3 to the fourth is equal to 81. A lot of these are going to require a little bit of familiarity, just doing these problems over and over and seeing these patterns, or using calculators. So for this last one, let's do one that you can't do by hand, not easily. We're going to do log base 7 of 100. Oftentimes, logs aren't going to be pretty, and we're going to have an answer like 2.366 in this case. You're going to need a calculator to solve this. But logarithms are used in a wide variety of fields, from modeling in biology to chemistry, or even finance. But now you might be wondering, what does it mean to multiply 7 by itself 2.366 times? What even is a fractional exponent? Well, we're going to explore that in the next video, where we break down fractional powers and what they really mean. If this video made logarithms click for you, give it a thumbs up and consider subscribing for more math-based content like this. And with that, I'll see you in the next one.